Given the function f of x is equal to x times the square root of x plus 3, we're asked to find the inflection points of f. So the first thing I'm going to do is rewrite this function. I want to think of it as x times x plus 3 to the 1/2 power. And since I have a product of two things, I'm going to need the product rule. And in the process of using the product rule, when I take the derivative of the second factor, x plus 3 to the 1/2, I'm going to need the chain rule. So, first derivative, f prime of x, is going to be equal to 1 times x plus 3 to the 1/2 plus 1/2 x plus 3 to the negative 1/2 times 1 times x, where the 1/2 times x plus 3 to the negative 1/2 times 1 is the chain rule on x plus 3 to the 1/2, and the x at the end here is the x that we didn't change from before. So cleaning this up just a little bit, we will get x plus 3 to the 1/2, and we will get plus 1/2 x times x plus 3 to the negative 1/2. Moving on to take a second derivative, we're going to get 1/2 x plus 3 to the negative 1/2 times 1 from the first part. Second part's going to need a product rule. We're going to have 1/2 times x plus 3 to the negative 1/2. That 1/2 in front is the derivative of 1/2 x. Then we're going to have plus negative 1/2 times x plus 3 to the negative 3/2 now, times the derivative of what's inside is 1, times what was out front, which is the 1/2 x. And if we work to clean that up a little bit, we're going to have 1/2 times x plus 3 to the negative 1/2 plus 1/2 x plus 3 to the negative 1/2. Those are the same thing. We're going to be able to combine those. Minus, we're going to end up with 1/4 x times x plus 3 to the negative 3/2. So let's write this as 1 over x plus 3 to the 1/2 minus x over 4 times x plus 3 to the 3/2, where this first term I get by combining the first two terms of the previous expression. Half of x plus 3 to the negative 1/2 and half of x plus 3 to the negative 1/2 is 1 x plus 3 to the negative 1/2. And then trying to make all of my negative exponents positive by putting things into denominators. So if I put this over a common denominator, I'm going to end up with 4 times x plus 3 minus x divided by 4 times x plus 3 to the 3/2. So what I'm noticing here is that the first expression is missing a 4 in the bottom and a full x plus 3. X plus 3 to the 1 are 2/2. So we multiply top and bottom, and that gives us this. Now, I'm going to end with 4x minus x, that's 3x plus 12 over 4 times x plus 3 to the 3/2 power, which is equal to 3 times x plus 4 all over 4 times x plus 3 to the 3/2 power. That is quite a derivative, and we're going to need an extra page here to go on and find our points of inflection. So let me create an extra page here real quick. We'll add one in, and we'll go there. Now let me flip back just for 1 second and make sure that I can write this down. So f double prime of x we have found to be 3 times x plus 4 divided by 4 times x plus 3 to the 3/2. Now let's go back just for a second and take a look at the original function. Now it has a square root in it, and this square root can be negative, and we don't ever want to take square roots of negative numbers, at least not in this calculus course. We only want to deal with real numbers in this course. So we don't want to ever deal with anything that is less than negative 3. So our domain is going to be numbers that are negative 3, excuse me, and larger. So let's write that down here so we can remember that. The domain of our function was numbers negative 3 to infinity. So now let's take a look at where we get zeros of the second derivative and where it's undefined. It's going to be undefined when x is less than negative 3 again. Or actually in this case, in both exactly at negative 3. But that's a boundary of our domain. So we're already going to kind of pick that up from the domain part of things. We don't really necessarily need to pick it up as a 0 of the denominator. We're also going to pick up x equal negative 4 as something to worry about. So when we create our sign chart here, we're going to kind of cap this end at negative 3. And then when we go to put negative 4 on it, well, it doesn't fit. There's no place for negative 4 to go. So that says this thing's going to have the same concavity on it everywhere. That is, the concavity cannot change. The bottom, for numbers that are greater than negative 3, all right, it has to be positive. And the top, for numbers that are greater than negative 3, also has to be positive. So the concavity is positive, therefore it is concave up everywhere. Graph the function, see what you see. But this will not have any points of inflection, or inflection points if you prefer, because concavity never changes for this function. So another one of those weird problems, we haven't seen many, but we see them once in a while, where we do an awful lot of work looking for something that it turns out isn't even there. But calculus tells us it isn't there, and it tells it to us very definitively.